Under Moore's law, integrated circuit technology has hit physical limits, and to break through, we must turn to light, which is why many companies are actively investing in silicon photonics. The fusion of electronics and photonics solves signal transmission loss issues and may become key to extending Moore's law and transforming the future. Integrated circuits pack thousands of transistors onto a chip for complex computations, while silicon photonics integrates optical circuits, concentrating light-guiding pathways. Simply put, on a silicon platform, it converts electrical signals into optical signals for electro-optical signal transmission and chip-to-chip communication. With advancing technology and faster computing, this has become critical for computing speed, especially now as we enter the AI era, where silicon photonics boosts optoelectronic transmission speed and addresses signal loss and heat issues in copper-based components, making it favored by semiconductor giants investing in related R&D. Before discussing silicon photonics applications and challenges, let's first understand how optoelectronic transceivers work. Imagine an optoelectronic transceiver as a rectangular USB module plugged into a computer to read data. In other words, optical signals must enter the module to transmit signals to the server. Traditional pluggable modules contain many optoelectronic components. When optical signals enter, a photodetector receives the light. Since light generates a small current, an amplifier boosts the current signal and converts it to a voltage signal. The electrical signal enters the host and meets a switch, which processes and converts the electrical signal, determining its output path. And after passing through a modulator paired with an RF light source input, the electrical signal is converted back to an optical signal. This is the concept of an optoelectronic transceiver, which includes photodetectors, amplifiers, modulators, and more. In the past, these components were scattered on a PCB, but to improve power efficiency and signal speed, they're now integrated onto a single silicon chip. We say essence because optoelectronic signal conversion on a silicon platform falls within silicon photonics scope. To better understand, let's review the stages of silicon photonics development. Traditional pluggable modules resemble USB interfaces with two fiber optics for incoming and outgoing signals. But electrical signals in these modules travel a long path to the switch, causing high losses in fast computing. To reduce electrical losses, photonic components are placed near the server's switch, shortening the electrical signal path, leaving the pluggable module with only optical fibers. This approach is the industry's focus, co-packaged optics technology, which integrates electronic and photonic circuits on the same substrate, forming a combined chip and module package to replace optoelectronic transceivers. This brings the optical engine closer to CPUs and GPUs, shortening electrical paths, reducing data transmission loss and signal delay. According to the ITRI, this technology cuts costs, boosts data transmission 8-fold, provides over 30 times the computing power, and saves 50% of power consumption. Though chip integration is still a work in progress, and advancing this technology is the next critical step for silicon photonics. Currently, silicon photonics addresses signal delay in pluggable modules, but as technology evolves, the next phase will tackle electrical signal issues in CPU-GPU transmission. Academia notes that chips mainly use electrical signals, so the next step is enabling GPU-CPU communication via light, converting all electrical signals to optical for faster parallel computing, addressing current computing bottlenecks. As technology progresses further, we'll enter the all-optical network era. Japan is actively investing in all-optical networks with silicon photonics. Moore's law predicts the number of transistors on a chip doubles every 18 to 24 months due to process technology advancements. But since chips use electrical signals, signal loss remains an issue. And even with more transistors per area, electrical signal loss persists. However, silicon photonics technology uses optical signals for high-speed data transfer, enabling higher bandwidth and faster processing. So chips no longer need more transistors or smaller nanometer nodes, achieving greater efficiency on existing silicon processes. This further drives Moore's law. With high bandwidth, small size, low power, and cost benefits, silicon photonics holds great potential in communication and high-speed computing. It can be applied to biomedical sensing, quantum computing, machine learning, and LiDAR. Take LiDAR as an example. For level 4 to 5 autonomous vehicles facing complex environments, signal processing must be extremely fast. LiDAR sensing based on silicon photonics is a promising breakthrough approach. These applications will bring revolutionary changes, advancing technology in communications, healthcare, and science. However, silicon photonics faces challenges in component integration. First is the interface communication issue. While semiconductor firms understand electrical processes, photonic components are sensitive to temperature and path. Line width and alignment greatly affect optical signals, Developing efficient photonic structures and processes requires a communication platform for design specs, materials, and parameters, integrating optoelectronic vendors' information. In the short term, silicon photonics targets niche markets, with packaging processes and material standards still being established. Most foundries offering silicon photonic wafers provide customized services or restrict access to other vendors. The lack of a unified platform may hinder photonic technology growth. Beyond the lack of a common platform, high manufacturing costs, light source integration, component performance, material compatibility, thermal effects, and reliability are also bottlenecks in silicon photonics. With ongoing technological advances, these bottlenecks are expected to be overcome in the next few years to a decade. Silicon photonics is advancing in multiple directions, with expanding application fields. Its future potential is worth anticipating.